Our today's chapter is chemical kinetics. General introduction. There are following three main aspects related to the study of reaction. Whether the reaction at all take place or not, spontaneity of a reaction as discussed in terms of use free energy change in thermodynamics. Second is if the spontaneous downward to extend the reaction take place before equilibrium is attained. Third is rate or speed of a reaction, which are a branch of thermodynamics is unable to answer. For example, thermodynamics predicts that the conversion of diamond to graphite is feasible, but the process is too slow that change is not predictable at all. Hence, most people think that diamond is forever. Besides studying the rate of reaction, we are also interested to know the factors of which rate of reaction can be altered. The study of the rate of reaction, which helps us understand the pathway from the reaction to products. Called mechanism of reaction, the branch of chemistry which deal with the study of a speed or rate of chemical reactions, that factor affecting rate of reaction and the mechanism by which the reaction process is called known as chemical kinetics. In this unit, our main aim to will to discuss mean by the rate of reaction, factor on which rate of reaction depends on mechanism of reaction. Also study of effect of concentration of the rate of reaction, which give the new term called order of reaction, which will be discussed in later. Further, to explain the mechanism of reaction at the molecular level, we discuss the theory of collisions of molecular collision theory. Classification of reaction on the basis of rates. Besides upon the rates, various chemical reactions are classified into three types. First is a very fast reaction which take place intensely, called ionic reactions like AgNO3 plus NaCl, and after reaction AgCl plus NO3. Second is very slow reaction which may be take place a day or month. Example, rusting of iron. A third reaction which can neither be very slow or nor very fast take place at moderate speeds are called very slow reactions. Example are hydrolysis of ethyl acetate. CH3COC2H5 plus H2O, then after reaction CH3COH plus C2H2O5. Other examples are hydrolysis of sucrose. Third example is decomposition of ammonium nitrate and the decomposition of hydrogen peroxide. The main category of reaction for the kinetic study have been reaction belonging to category. Third is which neither very slow or very fast. Both rates difference in rate. An obvious reason is reaction involves the breaking and making of bonds, since different bonds require different amount of energy for breaking and different amounts of energy are involved with different kinds of new bonds are formed, and rate of reaction are different. The instantaneous rate or nature of ionic reaction is due to the fact that these do not involve any breaking of bonds. Another reaction for the difference in rate of reactions in terms of activation and energy. Rate of reaction and its measurements and dependence on various factors. First is rate of reaction. The rate of reaction means the speed of which reaction takes place. The speed of a vehicle is expressed in terms of distance traveled by per unit. The speed of a reaction is expressed in terms of decrease in the concentration of reactants per unit or increase in the concentration of product per unit time. Rate of reaction may be defined as the rate of reaction is change in concentration of any one of the product, reactant or product per unit time. Hypothetical reaction is reactant converted into product. Rate of reaction decrease in the concentration of reactant R by time travel or increase in the concentration of a product P divided by time interval. Then R1 and P1 represent the molar concentration of reactant and product respectively and at time t. R2 and P2 are respective concentration at time t2. Then the changes in concentration of reactants and products. And the rate of reaction is minus delta R by delta T or plus delta P upon delta T. Significance of negative and positive signs. It is emphasized that the rate of reaction is always positive. The main sign along with the first term is used simply to show the concentration of the reactant is decreasing. Delta R is the negative, and so that negative and negative means positive. The plus sign along with the second term is used to show the concentration of product is increasing. For example, consider the PCl5 is converted into PCl3 plus Cl2. In this reaction, delta PCl5 by delta T is equal to plus PCl3 by delta T plus delta Cl2 by delta T. Unit of the rate of reaction sign. Since concentration is usually expressed in mole per liter and the time is taken is second or minutes, the unit of the reaction is moles per liter per second. or mole liter inverse minute inverse. In case of gases, reaction pressure are used in place of mole concentration as pressure are expressed in unit atmosphere. Therefore, the unit of the reaction is atom for atmospheric minute inverse or second inverse. And so between partial pressure of the gas organization, PV is equal to nRT, N by V is equal to P by RT, and or C is equal to P by RT. V is equal to number of moles of gas by total number of moles and into total pressure. Second is average rate or initial rate of reaction. A difficulty arises in starting the rate of reaction in above. This is because according to the law of mass action, the rate of reaction depends upon the molar concentration of reactant which keep decreasing on the passage of time. Therefore, the rate of reaction does not remain constant thereout. Hence, the rate of reaction is defined above the average rate of reaction during the time interval chosen. The expression for the rate of reaction written as average rate of the reaction. Average rate of reaction is delta R upon delta T plus m in delta P by m delta T. In general, R average is equal to delta X by delta T. This is the instantaneous rate of reaction can be classified in the rate of reaction at any instant of time is rate of reaction change of a concentration per unit time of any one of the reactant or product or the particular instant of time. To express the instantaneous rate of reaction, a small interval delta t is chosen as a particular instant of time during which the rate of reaction is supposed to be almost constant. In fact, instantaneous rate of average rate during the smallest possible interval of time. Suppose the small change in concentration delta x is the small interval at that delta t. Rate of reaction is delta x by delta t. Instantaneous rate is equal to delta x by delta t. At delta t is equal to 0, is a measurement of the rate of reaction. In order to measure the rate of reaction, the progress of reaction is followed by the studying of concentration of one of the reactant or product at which interval of time. The most common practice so that we draw some small amount of reaction mixtures different interval of times called freezing of a reaction and find the concentration of the reactant or product by stable method, usually titration against the stable adjacent. This method is preferred when some variable properties like volume, pressure, optical rotation changes one time to observe directly in different intervals. If concentration of one of the reactant is studied at different intervals of time, these values are plotted against the corresponding time. A graph is shown in 4.1. You have to see calculation of instantaneous rate of reaction. To know the reaction at any instant t is the tangent draw to line a point, and the rate of reaction is change in concentration upon time. Delta x by delta t is equal to OA upon OB is equal to slope of the tangent. For example, for figure 4.1a is represent the case time theta is equal to 10 minutes and delta x is equal to 0.04 moles and delta t is equal to 20 minutes. Then rate of reaction is after 10 minutes is 3.33 into 10 raised to power minus 5 mole liter inverse second inverse. Calculation of average rate of reaction. To calculate the average rate of reaction between the two lines instant of say T1 and T2, the corresponding concentration x1 and x2 denominated, and the average rate of reaction is equal to minus delta R upon delta T is equal to minus x2 minus x1 upon delta T2 minus T1. And average rate is 0.0018 mole liter inverse meter inverse. Calculation of rates from the plot of concentration of a product varies with time. If concentration of one of the product is plotted against time, the time obtained is shown in figure 4.1c. The average rate of reaction between the time 1 and time 2 find to be noting concentration x1 and x2 corresponding to these lines shows in the lower part of the figure 4.1, and thence calculating the average rate is done above. And the rate of reaction is OA upon OB is equal to delta x upon delta t is equal to slope of the tangent. Factor affecting the rate of reaction. The rate of a particular reaction depends upon the following factors. First is nature of reactants. Consider the following two reactions. 2 and no plus O2 is equal to 2 and no 2 is fast, and 2 CO2 plus O2 is equal after reaction to CO2. This is slope. This reaction number 2 is similar to first was fast, and second is slow. And second is concentration of the reactant greater the are the concentration of reactant. First is the reaction. Generally, in the concentration of the reactant decreases, the rate of the reaction also decreases. Temperature. The rate of reaction decreases with increase in temperature. In most of the cases, the rate of reaction becomes nearly double to the 10 raised to power 6 rise to temperature. Pressure of the catalyst. The catalyst generally increases the speed of the reaction without itself being consumed in the reaction. If the surface area of the reactant for a reaction involving a solid reactant or a catalyst, and the smaller is the particle size, greater is the surface area and faster is the reaction. Six is presence of the light. Some reaction do not take place in the dark but take place in the presence of the light. Reaction are called photochemical reactions. Now we will discuss the quantitative effect of a concentration of a temperature and a quantitative reactions and mechanism of the reaction. This is step to discuss in the following sections. Dependence of rate of reaction of rate law, expansion and rate constant and order of reaction. Rate law and rate constant as chemical reaction depends the concentration of the reactor kept on decreasing while those of the products keep on increasing action. But graphically in figure 4.2, however, the rate of reaction is also found to decrease. This shows that the rate of reaction is directly due to the concentration of reactant. The effect of concentration of the reaction rate of reaction was studied at Goldberg and Weiss in 1867. They put forward the following results and the rate law of mass action. General reaction alpha A plus beta B is equal to products rate directly proportional to the A concentration of alpha and B concentration of beta. Where proportional constant is K, where A and B are the mole concentration and A B respectively K is constant, while viscosity, velocity constant or rate constant. The above expression is called the rate law. Like the expression which expresses the rate of reaction in terms of mole concentration of reactant, which term raised to at some power which may be or may not be same, and the stoichiometric coefficient of the reaction is a balanced chemical equation. This leads to the conclusion that rate law and any reaction cannot be predicted simply by looking at the balanced chemical equation. Theoretically, has been determined experimentally, mean concentration of A is equal to concentration B is equal to 1 mole per liter, and rate is K. And that may be defined as the rate of reaction which the mole concentration of reactant is taken as unity. This is why the rate of specific reaction rate. Concentration characteristic of rate of reactions rate constant is measured as the rate of reaction. Rate is the value of the rate constant. First is the reaction. Each reaction has a definite value of the rate constant at a particular temperature. That is, the value of rate constant for the same reaction changes with temperature. The value of rate constant of a reaction does not depend upon the concentration of reactant. It is the unit of the rate constant depends upon the order of reactions. The rate of rate law and the rate law of mass action. Rate law differs from law of mass action. In fact, whereas rate law states that the rate of reaction depends upon the concentration term, and the rate of the reaction actually depends on the rate law of mass action is simply based upon the stereochemistry of reactions. Rate law rate is right proportional to K into concentration of alpha and B concentration of beta. According to the law of mass action is equal to rate is equal to K into A concentration of alpha and B concentration of beta. The sum of the exponents of reaction, the sum of exponents powers to which the molar concentration and rate law equation are raised to express the observed rate of the reaction is called order of reaction. For example, the 5Br2 aqueous plus Br03 negative plus 6H positive after reaction that form the 3Br2 plus 3H2O. In this reactions, order of reaction is 4. So one common example of different orders is photosynthesis of HCl. This may order of a reaction of order 0 order, and the dissociation of N2O to 5 N2 5 after reaction rate form the 4 NO2 plus O2. The rate of reaction is first order, and the combination between NO2 plus F2 then is the second order reaction. And in the reaction of mathematical is fractionable. CH3CHO after reaction rate form the CH4 CO2. In this order reaction is 1.5. Some other example of different orders. Reaction of 0 order. Some enzymes catalyze reaction and reaction occurring on metal surface Of reaction zero order, decomposition ammonia on hot plate surface at a high pressure. This is the example of zero order. And second example is thermal decomposition of HI on gold surface. These are the example of zero order. And the reaction of first order is decomposition of ammonium nitrate, and the second example decomposition of hydrogen peroxide. Third is decomposition of SO2Cl2. Fifth is hydrogenation of ethane. Fifth is decomposition of N2O5, decomposition of NO2, N2O. Seventh is natural and artificial decay of unstable nuclei. See reactions of second order, decomposition of HI. Second is spontification of ethyl acetate. Third is reaction above between NO and O3. In this reactions order is second. Reaction of third order. First example is combination of N2 and O2 to form NO2. Combination second is combination of NO and Br2 to form NOBr. C is reaction of fractional orders. A reaction is between H2 and Br2 to form HBr. Second is combination between CO and Cl2. Third is decomposition of COCl2, in which reaction is fractionable. Unit of rate constant or specific reactions rate for different orders. In general, rate of reaction is nth. Rate is dx upon dt. It is equal to K concentration of n. And the formula is concentration inverse 1 minus n time inverse. Order of reaction for zero order: mole, liter inverse, second inverse. First order, second inverse. Second order, liter, mole inverse, second inverse. Third order, liter square, mole inverse, square, second inverse. In case of gas state, zero for zero order at atmospheric, second inverse. First order, second inverse. Second order atmospheric, inverse or second inverse. Or third order is atmospheric, inverse, square or second inverse. You have to see in some exit problems for practice. Distinguish between the rate of reaction or reaction rate constant. Rate of reaction, the rate of reaction is change in concentration of reactant or product per unit time, and the reaction rate constant is constant of proportionality in the rate reaction equation is equal to the rate of reaction when the molecular concentration of each reactant is unity. Rate of reaction, the rate of reaction is any constant of time depends upon the molar concentration of reactant at that time. Or reaction rate constant, the rate constant is constant for a particular reaction at particular temperature and does not depend upon the concentration of the reactant. Third is rate of reaction is units liter inverse time inverse, and the rate of unit for depends upon the order of reaction. Molecularity of a reactions, the reaction which take place in one step are called elementary reaction. Reaction which do not complete to take place in one step are called complex reaction. The different step in which complex reaction take place in is called mechanism of reaction. Step of mechanism of reaction, elementary reactions. According to the collision theory, the number of atoms, ions or molecules that must collide with one another simultaneously, so the result into the chemical reaction is called the molecularity of the reaction. In case of simple reactions are called elementary reaction, there is ions or atoms present in the balanced chemical equations, hence the molecularity is simply the sum of the molecules of reactants. A few examples are decomposition of O2F2. The balance equation is O2F2 rotation and form the O2 plus F2. And this is molecular reaction is 1 and the reaction is unimolecular. And the dissociation of HI to HI after reaction and form the H2 plus I2. And the molecularity is 2 and the reaction is bimolecular. And third is reaction between NO and O2. The balance equation is 2NO plus O2. Then it forms the 2NO2. This molecularity is C and the reaction is trimolecular. It is impossible for 12 ions reactant to come together simultaneously to collide. Each reaction are complex reactions. These reactions are supposed to take place in the sequence of a number of steps. Each of the step reaction is the elementary reaction. Molecularity can be defined only the elementary reaction. It is no meaning for a complex reaction. For the different elementation of complex reactions do not take place at the same time. The overall rate of reaction depends upon the slowest step. The slowest step is the rate determining step. The situation is similar to the cyclic factory. The different sections of the factory Manufacture different parts like handles, pedals, rims, seats. The overall number of cycles manufactured per day depends upon the slowest working section of the factory. This is obvious. The molecular variation must always be whole number, whereas the order of variation may be zero or fractional. Here, the order of reactions has always to determine experiment to find the exact power of the molecular concentration of for reactant at which reaction actually depends. This mechanism of reaction, as mentioned above, in case of complex reaction involving a large number of molecules of the reactants balance equations, a series of steps, reactions or elementary reactions proposed to account for reaction is called the mechanism of reactions. The writing of the steps of the reaction is usually based upon experimental evidence, the detection of the presence of some short-lived intermediates. This written in the rate law equation. Further, the sum of the sum steps justify the overall stoichiometry of the reactions. Some examples are: the first is thermal decomposition of dinitrogen pentoxide. The balance equation can be written as 2N2O5. Then after reaction, then it forms the 4NO2 plus O2. In this first step, there is N2O2, N2O5 is slow reaction N2O3. And second reaction is fast N2O5 plus NO3, then it forms the 3NO2 plus O2. The above reaction is unimolecular reaction. Reaction is first order reactions. Second is combination of NO2 and F2 to form the NO2F. And steps are 2NO2 plus F2 after reaction to form the 2NO2F. The first step is NO2 plus F2 is slow and that form the NO2 plus F plus F. Then second step NO2 plus F after fast reaction, then it form the NO2 plus F. This is bimolecular reaction or a second order reaction. Third is reaction between NO2 and CO2 and CO2F NO. In this NO3 found a smaller amount and the above reaction is bimolecular reaction and reaction is second order. Third is the decomposition of hypochlorite, in which 3ClO negative after formation, then it forms the ClO3 negative plus 2Cl negative. Experimentally, first step is ClO negative plus ClO negative. From the slow reaction, then it forms the ClO2 negative plus Cl2, and second step ClO2 negative plus ClO2 negative, then form the ClO3 negative plus Cl negative. In this reaction is order reaction is 2. In this second order reaction. There are problems for practice. You can solve these examples. Difference between the order of reaction and molecularity of reaction. It is the sum of the concentration of terms on which the rate of reaction usually depends on which the sum of exponent the molar concentration in the rate law equation. The molecular reaction, it is the reaction number of atoms ions that must be collide with one another simultaneously, so as a result in the chemical reactions. It is not to be whole number, it can be fractional as well as zero. It is always a whole number, it cannot be zero or fractional. It can be determined experimentally only, the cannot be calculated. It can be calculated by simply adding the molecules of the slowest step. Order of applicable is elementary as well as complex reaction. Molecularity is applicable only to the elementary reaction. The overall molecularity of reaction has no significance. It is only the slowest step whose molecularity has significance for the overall reaction. Molecularity of the slowest step is the same as the overall reaction of the step. Rate of reaction is a balanced equation, and the based on the molecularity of reaction is based on the stoichiometry of the reactions. Integrated rate equations have already discussed. The general equation is alpha A plus beta B is equal to, after reaction form the C beta or D. In the form of equation is differential rate equations. Integrated rate equation for zero order. This is the mathematical formation. Then after it form the KT, A concentration of A naught concentration minus A concentration, or K is equal to 1 by T in bracket A naught concentration and A concentration. Some important characteristic of zero order reaction. Any reactions of zero order must obey equation. Second equation is straight line y is equal to mx plus c. We have to see in figure 4.5, 4.6 and 4.7. 4.5 plots A versus T for the reaction of zero order, and 4.6 plots the rate versus concentration for reaction of zero order, and 4.7 plots the graph 1 by 8, 1 by half, T half versus initial rate of zero order reactions. Half-life period T half is the time in which half the substance has reacted. And the formula for T half is A naught concentration by m2k. The half reaction is zero order is direct proportional to the initial concentration. Unit of the rate constant is mole liter inverse time inverse. And to solve these problems on zero order reactions. Integrated rate equation for first order reactions. A reaction is said to be first order if rate of reaction depends upon the one concentration term only. A converted into the product and rate of reaction is direct proportional to the A. Concentration to A. Rate of concentration depends upon the A. A converted into the products and the mathematical formation for the first order reaction, and last answer is K is equal to 2.303 upon m T log A minus K. A by m A minus X. The exponential form is A concentration is equal to the A naught concentration E exponential power is minus KT. Some important characteristics of first order reactions. Any reaction of the first order reactions must obey reaction 6, 7, and 8. So B is substitution method. Second is the graphical method. We plot the graph for first order reactions. You have to see in for figure 4.9 for the plot of graph log A concentration versus T. Second is half-life period. The time taken for any fraction of the reaction is to complete the independent of the initial concentration. For example, T is equal to m2 minus 2.0303 by m K log m by m A minus X, and T half is equal to m 0.693 by m K. And for first order gas phase reactions, in which answer is K is equal to 2.303 by m T log P naught by m P theta by minus Pt. The half-life period for reaction, the time taken for half of the reaction to complete the time is in which the concentration of the reactant is reduced to half to original value is called the half-life period of the reactions. T half is equal to 1 by m A theta raised to power n minus 1. You have to see in problems to solve this. Remind the rate of rate law, rate constant, and order of the reactions. First is graphical method. For using differential rate of air, this method is used when the only one reactant converted into the product. This is the zero order reactions. Use differential rate methods for the timing. Figure 4.11. You have to see in table 4.1 for the data of decomposition of N2O5. And figure 4.13 plots the rate versus N2O5 and B rate versus N2O5 square. K is equal to rate by me N2O5. And the problem second is initial rating method. The method can be used in respect to the number of reactants involved consider the reactions N1A plus N2B plus N3B that is converted into products. This method consists in finding the initial rate of reactions, taking known concentration of the different reactions ABC, the concentration of one of the product in J is taking the concentration of the reactants B and C same as before. The initial rate of the reaction is determined again like this gives the expansion with respect A and hence with respect to A. The experiment is concentration C and concentration is obtained. Suppose it first is keeping the concentration of B and C's concentration of A is doubled. The rate of reaction becomes 4 times the reactions A is tripled. And the rate of reaction is 9 times. Keeping the concentration A and C of the concentration B is double, the rate of reaction is also doubled. Keeping the concentration of A and B is constant, if concentration of C is double, the reaction is often factored, and C is 0. Continually, it is ordered of respect A, B, and C, and alpha, beta, and gamma have been seen. Alpha is equal to may log r theta 1 by may r theta 2 divided by the log a theta 1 by may divided a theta 2. The order of our order of variation is alpha plus beta plus gamma. And the rate of variation is only a concentration. Rate of any time at which found plot of concentration versus time slope of the tangent on the curve at any times gives the rate of variation at time. It involves differential of the concentration with the time to express the rate. This method is called Wohlhaus differential method. Third is integrated late law method. This is the most common method studying kinetic of chemical reactions. Consider the NA converted in the products. If reaction is first order dx upon dt is equal to k into may a minus x, or second order dx by dt is equal to k into may a minus xk. For the first order k is equal to 2.303 upon t log into may a naught concentration by may concentration. The advantage of integrated method is to these integrated terms forms of equation contains the concentration of reactant at different times, hence can be solved to find the value of k and data of the run of one experiment only on need not start with different initial concentration. Moreover, they can be used at time connection to complete. First is substitution method. The result of the experiment and substituted in the expression and for rate of reaction different orders one by one. The expression which gives a constant value for the rate can decide the order of reaction is the limitation of this method is over the here and trial method. In this graphical method, the above expression can be listed by the graphically. Fourth is half-life method. Already discussed, the half-life period of reaction is nth order, related to the initial concentration of the reactions. A substitution method starting with two different initial concentration of the finding half-life order of reaction can be calculated is equal to n is equal to plus 1 plus log t half 1 or minus log t half by 2 by me divided by log a concentration 2 minus me log a concentration of 1. Means graphically method half-life pyramid can be used to order of reactions. K is proportionally constant, not be rate constant. For the zero order reaction is testing figure 4.15. There is testing order of reaction graphically by half-life method. Fifth is Oswald isolation method. This method is used when the reaction number of reactants or reactants except one or taken in large excesses interchange concentration is negligible and rate of reaction depends only in the concentration taken in the smaller amount. Alpha A plus beta B plus gamma C is converted in the products. Reaction A is found similarly the order of respect B and C determined or reaction can be determined. Example of the reactions for first order decomposition of nitrogen peroxide. The compound nitrogen pentoxide is a volatile solid which decomposes its gas state as well as in form of solution in inert solid like carbon tetrachloride chloroform according to the equation N2O5 then converted to N2O4 plus may half O2 N is converted into to NO2. Volume of the oxygen gas collected at any time with in right amount of N2O5 decomposes volume of oxygen as collected at any time with right proportion the amount of N2O5 decomposes X is right proportion to VT. And the overall first order reaction is get is equal to 2.303 upon T log A by AX and the T is equal K is equal to 2.303 upon T log V infinity by V infinity minus VT. Constancy of value K proves the reaction of the reduced first order. Problem, this is a simple problem 1. You have to solve this. Second is the decomposition of ammonium nitrate. An aqueous solution of the ammonium nitrate any moderate temperature decomposes according to the reaction and H4NO2, then it is converted into H2O plus N2. Third is decomposition of hydrogen peroxide. Decomposition of hydrogen peroxide is in aqueous solution is catalyzed by finally taken place according to the equation H2O2, then it converted to H2O plus may half O2. Which K is equal to 2.303 upon may T log A by A minus K, or K is equal to 2.303 upon T log V theta by may Vt. Next is pseudo first order reactions. Consider the general reactions A plus B, then it converted in the product in which order with respect to reactant is 1 is OR reaction is 2. However, one of the reactants is present in large excess, one of the reactants can be solvent and its concentration will remain almost constant. In this case, the rate of reaction will depend only on the concentration of reactant present in the smaller amount. This reaction becomes first order reactions. So reactions which are not really for the first order but under certain conditions becomes reaction of the first order are called pseudo first order reactions. Example are acid catalyzed hydrolysis of ethyl acetate. Second is acid catalyzed inversion of sugarcane. Sugarcane formula C12H22O11 sucrose plus में H2O hydrogen peroxide converted in the glucose and factor C6H12 plus O6. And it is kinetics of been studied. The hydrolysis of ethyl acetate CS3CO C2H5 plus H concentration, then it form the CS3COH plus C2H5 OH, in which K is equal to 2.303 upon T log V infinity minus V theta by V infinity minus Vt. Second is conversion of sugarcane sucrose hydrolysis. Sucrose is present in the mineral acid takes place according to the equations C12H12. So in important characteristics of the reaction in sucrose is dextrorotatory, whereas the products glucose and fructose is dextrorotatory and levorotatory respectively. The levorotatory of the fructose is more dextrorotatory of the glucose, so that the mixture is whole levorotatory. This is the hydrolysis of dextrorotatory sucrose gradually changes into the levorotatory mixture. It is for this reason reaction is inversion of sucrose. Reading of the polymerase at 0 time R naught, reading of the polymerase at time t is equal to RT, and reading of the polymerase at infinity time R infinity. This is the evident that shows the later carefully considered shows the angle of rotation at constant of time R naught minus RT is not the amount of sucrose hydrolyzed R x is in direct proportion to R infinity minus RT. And the overall K find the 2.303 upon T log R theta minus R infinity by RT minus R infinity. The application of this reaction is about the inversion of sucrose is shown by the Wesley 1850 study. Noted the actual value of K, the of course depends upon the concentration of H positive ions. Figure 4.16 is the reading of the polarimeters. The next is the threshold energy. The minimum energy which the colliding molecules must have in order that collision between them may be defective is called threshold energy. At room temperature, most of the reactions molecules have energy less than the threshold value. However, energy is supplied in the form of heat light. The reactant molecules absorb this energy and their energy becomes equal to the greater than threshold value. Hence, they start reading and change into products. The next is the activation energy. The minimum extra amount of energy absorbed by the reactant molecules to their energy becomes equal to the threshold value is called activation energy. In this order, activation energy is difference between the threshold energy and average kinetic energy of the reactant molecules. Activation energy is equal to threshold energy minus average kinetic energy of the reactants. Evidently less is the activation energy, faster is the reaction, or greater is the activation energy. Slower is the reactions. For example, 2NO plus O2, then it form the 2NO2 in the first reaction. This was the low activation energy, where the reactions 2CO2 plus O2, then it form the 2CO2 is similar. Slow reaction is higher activation energy. We have to see in figure 1.47. Reaction profile of the isothermic reactions. Reaction profile was followed by the reactions or concept to activation complex transition state. In order to reaction may change into products, they have to cross energy barrier corresponding to the threshold energy. This figure has been obtained by plotting potential energy versus reaction coordinate. Reactions coordinate represent the reaction profile. Process of reactions from reactant to product accompanied by the changes in potential energy. It is believed that when the reactant molecules absorb energy, their bonds are loosed and new loose bonds are formed between them. The intermediate thus formed called the activated complex or transition state complex. Seen A bond A plus may be bond B. Reactants then that form the activated complex that form the 2AB is the product. It will note that when the activation complex dissociates from the product is accompanied by the release of energy, but the enthalpy dilates during the reaction is that particular temperature remains the constant because it depends only on the nature of the reactant and the shown in figure 1.7. Threshold energy is called activation energy plus energy processed by the reactants. Temperature dependence of the reaction of the effect of temperature on rate constant Arrhenius equation. Temperature has a marked effect on the rate of reaction. For most of the reaction, the rate of reaction is becomes nearly doubled or even more. For 10 raised to power 6 rise of temperature, the effect of temperature is usually explained in terms of temperature constant, which is defined by the equation. Temperature coefficient n is equal to rate constant at a time t plus may 10 raised to power n, that is 308 Kelvin. By may rate constant at time t or its temperature is 298 Kelvin. Motion reaction to 3 is greater than n and n is greater than 2. Explanation as already explained, for the collision to be effective or collision molecules must be energy more than threshold energy at the particular temperature. T, all the reacting molecules having a particular kinetic energy at a particular temperature becomes constant, and at a particular temperature fraction molecules are plotted versus corresponding kinetic energy. Graph of this type shown in figure 1.9 obtained called the Maxwell distribution energy. The peak of the curve represents the kinetic energy processed by the maximum fraction of molecules. It is called most probable kinetic energy. The point A represents the threshold energy. The shaded area ABC represents the fraction of molecules having energy greater than the threshold value. When the temperature is increased to the T plus may T half, the curve shifts as shown in the figure 1.19. The fraction molecules having kinetic energy greater than the threshold value is represented by the shaded area. ABCDF mainly is due to the increase in the number of effective collisions. Remember that the increase in the rate of reaction which rises in temperature is due to the increase in the total number of collisions due to the increase in the total number of effective collisions. Now the increase of temperature peaks shift forward the downward. This means with the increase in temperature, first is the most probable kinetic energy increases, second is the fraction of molecules possessing most probable kinetic energy decreases. Quantitatively, the effect of temperature on the rate of reaction hangs on the rate constant K, the proposed by the Arrhenius in 1889. The equation called the Arrhenius equation. This is usually written as in the form K is equal to AE by 10 raised to power EA by RT.